Hi there, thanks for joining. My name is Ethan, and I am creating this video to demonstrate my programming project from the summer of 2016. So this project was initially inspired when I first became familiar with agent-based modeling. For those who don't know, agent-based modeling is a class of modeling where you take numerous low-level agents or individuals, place them within a system, and then together these low-level agents will interact within this environment, and a sort of higher level pattern or behavior will begin to emerge that isn't explicitly defined in the program. Uh, a classic example that exists in biology that I'm familiar with is termites and the mounds that they make, which are skyscrapers relative to their size. And these things are engineering marvels, really. They have proper ventilation, regulate temperature, have a complex system of tunnels and passageways to best protect the queen in case of an attack. And there's no one architect or one brain that's overseeing the construction of these mounds. It's just a bunch of these low-level termites responding to basic sensory input, and together working to create these mounds, which are their homes. So one of the first things that popped into my mind when I became familiar with agent-based modeling was just the behavior of the stars and planets and galaxies of the universe, particularly sort of the orbital behavior that emerges um, across all these varying celestial objects of different masses, where there's no explicit rule that says the Earth must revolve around the sun, but it's really just a behavior that emerges as a result of simple Newtonian physics, where on one hand you would the planet, say, bypass the star and have its momentum, have it keep on moving in a steady direction, but then the force of gravity pulls it back in, and the resulting vector between those two different phenomenon is the orbital path that we observe. So that's kind of what I've done with my app here. The idea is I can just place different objects within this system and just let them go, and then this behavior of different masses sort of tugging at each other begins to emerge. So if you see here, bottom left, I have different planet types of different masses that I can place within my system. So for example, I can just go and place my star, which is a larger mass, take a planet, click and drag to give the initial velocity, and I'll see that planet just begins to sort of loop around. Force of gravity from the star begins to pull in that smaller mass. I also have dwarf planets here, which are given us a smaller mass, and you'll see that they begin to get dragged in a lot quicker because of the force acting on that smaller mass is in fact larger. So it can be fun to sort of just play around and to see it respond live. Something else I can do is, for example, place multiple stars within the system and have them just sort of dance around each other. You see there's obviously a collision detection feature in here as well. I also have these blue giants, which are extra massive stars, and they're explicitly defined to not move. So that's why you don't see them being attracted to one another here. But again, you can just sort of place objects within the system and see them respond accordingly and sort of dance around these large objects that we have here. Could also go, and if I perfectly split these two blue giants, we'll see that we sort of make it through clean, because the net force acting on that dwarf planet is a sum zero, and so we'll just go through clean. One other planet type that you'll see in here is this orbit type, and what that will do is automatically find the nearest star in my system and calculate the proper initial velocity so that it orbits the nearest star and maintains orbit. But of course, if I go and introduce another object in the system, then the orbital path is broken from that force, and then we get that behavior that we see here. So I guess one of the cooler things we can demonstrate is if we place a star, give a bunch of different planets which go in orbit that star, then introduce another mass which will compete, and then everything just begins to move. So that's sort of a basic demo of the operation of the program here. Now we'll begin to actually dive into the code and how it works. So this program utilizes the Qt graphics libraries. I guess one of the big things to note about Qt and how it operates is its method of signals and slots for different objects to communicate within this graphics environment and respond to one another. So as an example, I'll just show, let me go to my button class here. So this is a Q object, and we see we have this signal that we define whenever the button is clicked. So if I hop into the file here, oops, button CPP. So whenever we have this mouse press event, a defined Q graphics function, we'll go and emit this clicked signal. And then what we'll do is link it up to its appropriate slot function, which are these guys right here. Go back to my button.h, you'll see these are the slots. We set our two colors. So now all I have to do is connect that signal to a slot, and I can show where that's done right here, for example. So if I go, and these are my different buttons right here, dwarf, planet, orbit, star, giant, and say I go and click the dwarf button, then through this connect function, this Qt feature right here, I will connect the signal of clicking the dwarf button to then setting its active color. Meanwhile, I'll go and then deactivate the colors of all the other buttons. So that's an example of just how signals and slots work within Qt. And you'll see as I move forward here that we heavily utilize this feature to have all of our objects communicate with one another. So to dive into the bulk of my program, we'll go to this GUI class that I have, and that's really the highest level class that encapsulates the entire program. The two main things or main classes features within the GUI class are my system and system virtual. So system is a linked list that will hold all of my sort of celestial objects that I place within the system, but that's as it pertains to the actual sort of physics of those objects. So I'll track the mass and velocity and acceleration, and it's within this system that actually sort of do the hard math and physics to process how these objects should move. Then the system virtual is sort of directly linked to the system, and it sort of represents the graphical display of the physical system right here. So that's where I'm actually then moving the objects accordingly based off the defined physics within the environment so that the user actually sees the response. So those are sort of the two big classes we have here. To go into some other things, you'll see these different members pertain to key variables that I'm utilizing as I'm going in and adding objects within the system. You'll also see this timer as well, which is key to actually running the program. This is the clock which makes this program run. And then the key functions within GUI itself are when I'm going in and actually clicking within the overall environment here, and adding objects to the system, giving them initial velocities, and so forth. So before I go into those key functions to see how we add to the system, let me first just highlight the class that we'll be adding, and that will be our celestial class right here. That's the actual physical object that we're adding to the system, the physical system. And as you see, we have defined mass, velocity, acceleration, and from the celestial class, our different planet and celestial types will be inherited from this overall class. So like our dwarf will inherit from celestial, our planet will inherit from celestial, and so forth. Now, as for the system virtual, that's where our body class comes into play. And you'll see that our celestial objects actually have a pointer to that body class, and that's what sort of preserves that link so that they can easily talk to each other within the various functions that we have, but still have two separate systems because we have different, well, as you'll see here, I have different threads going in and operating to process different things, and it helps avoid thread interference. But this link right here will allow the system and system virtual to communicate with each other. And this is just the body class right here. And this is just the actual Q graphics item. And again, the graphical representation that the user sees. And again, as you'll see here, just like with the celestial class, we have a pointer to a class of itself because it's part of a linked list. Now, let's go into actually adding in these celestial and body classes into our system and system virtual. So we'll go to this GUI class here. Again, this is the highest level class, which our entire program is encapsulated in. So just, I guess, to run through this real quick, this is just establishing our scene and environment. And then, as I mentioned before, we'll go and create these different buttons, which we will also add into our scene. And you'll see we also have these different threads that are going, and I'll dive more into this later on in the demonstration to explain how all those threads are operating. But what I want to highlight now is these different mouse events, because as we click, as you saw here, I'm going in and just adding in our objects into our system. So mouse press event, that's you know, a Qt function that we end up defining. So whenever we click the scene, this function is then called, and we go and define it accordingly. And so pretty much what we do is we nab the position of where we click, and then we'll go in, and based off, this just limits the amount of objects we have in our system. Based off the current button that has been selected, we'll go and then create the appropriate celestial object, and then we will set its position accordingly based off that position that we clicked. Lastly, we'll go in and add this into the scene. And then right here, we're marking that, hey, this, because I should know we're both making the actual celestial object and then its corresponding body. Then we'll go and sort of mark this to say, hey, this pointer to our celestial object and our body widget is what we're operating on right now, because right now I'm just defining the mouse press event, but we still need to operate upon our celestial and our body as we move the mouse around and then ultimately release the mouse. So we just take this first step here when we take this click, we just define our position. You also see here that we create this line, and that will operate on this line later in our our mouse move event function to help sort of represent the initial velocity that we're giving our objects. So let's move down to our move event. And here we simply, well, first we check to make sure it's a dwarf planet or star, because we don't want to give blue giants any velocity, and also orbits are given their own velocity based off their distance to the star. And I'll go and explain that later in the video. But pretty much right here when we're moving, all we want to do is move around the position of this line that appears based off where our mouse drags. And so what we do is just grab the current position of where our mouse is, and then we grab the current celestial object that we're operating on, its position that was saved previously in the mouse press event, and then we'll go and define the vector of our line so that the line will extend in the opposite direction of where we drag. And then in this get line, or this set line function right here, we actually go and establish that line and place it within the scene. Now lastly, the last mouse function is the mouse release event. And this is where we actually place we've already created the celestial object and the body widget, and this is where it actually gets inserted into our linked list. It's given its initial velocity, and then we'll, through processing of the threads, we'll then begin to move within the system. So you can see here, this is where we just calculate the velocity based off the position of our mouse relative to the position of where we initially clicked, the X position and Y position that we set before. And these two functions right here are when we go in and add the celestial object and the body widget into our system. It's the standard insert at the top of your linked list function, where we'll go and we'll set our pnext pointer to the head of the linked list, and then reset the head to the current object that we're adding in. And then again, just keep track of the amount of objects that we have in our system for processing limitations. So hop back to our GUI here. One other thing I want to note is, well, I guess also you see here that we remove and destroy that line that we'd created before. But this mutex right here, this you'll see this in subsequent functions as well. This is a class that helps protect this function from interference of other threads, and pretty much locks down the system momentarily so that other threads can't go in and interfere with what we're operating on. Because obviously, as we begin manipulating with our linked list, we don't want some other thread that's iterating through our linked list and causing conflict of interest and bugs that would ultimately shut our program down. So those are all the mouse events within our GUI class, and so you can pretty much see the sort of initialization of our program as we go in and add objects into our system. I still have to explain how we actually process their movement, but this covers the insertion of these objects into our environment. One other thing I want to speak to before getting to the actual mathematical processing of all of our objects is our orbit class right here. So again, this one's pretty unique from the other celestial types, and that we need to define a initial velocity. Well, first we need to find the nearest star and then define that initial velocity. So let me speak to those two functions right here, and that's where we our set star and calculate velocity. oops, not that one. Our, actually, excuse me, let me back up to our GUI where we actually call this. So if action equals orbit, okay, sorry, it's our find star. That's defined within our system. And that's where we go and find the nearest star based off where we clicked. And then this orbit function calculate velocities to calculate the initial velocity so that we'll maintain an orbit around the nearest star. And pretty much that's done by matching the force of gravity to the centrifugal force to then calculate the proper velocity. So if we go to find star, you see here we just pass in our orbit type celestial object. We'll, I guess, sort of a two-part function. First, we just determine if there is a star that exists within the system, and that's what's done right here. We start off by assuming that there isn't one. We then iterate through our linked list, and we find if, in fact, there's a star or a blue giant within the system, then we'll say it's true, and then we'll sort of just set an initial distance, which is, the running a little Pythagorean theorem right here, just the magnitude of the distance from our the star and the planet, and then we'll set that distance and save it for comparison later on. And this is where we then reiterate, once we've determined that a star is in our environment, we'll go through our entire linked list again. That's, with this ptemp equals ptemp get next, to then go and compare the distance of this orbit object we're adding in to every star. And then if we find that the distance is smaller, we'll go and reset it. And once that is done, we'll actually go and then call this set star function that I had mentioned before, and then set that star, save that star as the star in which our orbit object will orbit around. Now, the one other function from our orbit.cpp that we call is this calculate velocity. Let me dive into this. So again, this is just calculate the initial velocity. And again, it's from setting the gravitational force, which is it's going to be the product of the two masses over the distance squared times the gravitational constant here. And we're going to set that equal to the centrifugal force, which is the mass of the object which is moving around times its velocity squared divided by the distance. You set those two equations equal and solve for the velocity, and then you can calculate your velocity magnitude right here. And then we'll later go and, based off the angle that we're at, this theta value, we can then go and break that up into x and y components, because we're tracking everything here in both dimensions. One other thing to notice right here is our set radius and our set acceleration. So this is simply we're saving the distance from our star, the distance that we should be constantly orbiting at, in sort of a perfect circle, and then setting our acceleration. And that this is to sort of, this is later used as a measurement of error to determine if we break from our orbital path. And I'll explain more on that later, but take note of this for now. Now that I've gone over how the orbit type celestial object works when we place it into our system, I'll actually get into the processing of our environment. Let me go back to our GUI CPP, and I can speak to these threads right here. So this is a very process-intensive program, namely because to actually truly replicate the effects of gravity, I have to, for every object in my linked list, go and find the relative distance of every other object. So that's a nested loop right there, and then appropriately calculate the distance, and then update the acceleration, update its velocity, and then move those objects through the system. So it's very process intensive. And that's why I require these threads, so that I have these different processes that are operating independently here. So let me go and speak to my thread class right here. So this is a Qt class that I borrow from. And I have these different, well, I'll pass in my timer, my scene, and my two systems, so that the thread can appropriately operate in accordance with those. And lastly, I have this action member, and that is, we pass that action into the initialization of our thread when we create it to define what that thread is actually doing here. So we go to thread CPP, you'll see I have these 5 different actions defined here. And the one key function is run. And so if I go back to GUI CPP, you'll see where I run my threads, and that is done right here. I guess when we call start, we'll go into our run function here. So again, this timer is really what makes this program purr, I suppose, and can keep it going. We have it running at a frequency of every 25 milliseconds. So every 25 milliseconds, this timer will emit a signal, and then we'll go and appropriately link that signal to our desired thread, and that thread will run. And then it's, of course, going to run based off the action here that we've given it. So let's go through these threads one by one, and I can explain how we actually process our system. So if I go to our first thread here, this is where we have our detection collision. So this is defined within our system. Again, we're using this mutex here to avoid interference between other threads. And this function isn't too complicated and does borrow a Qt function to help with collision detection. It's pretty much, we have a double nested loop here. And so that's why we have ptemp and ptemp inner. And we're going to iterate through our system virtual. Sorry, let me just check upon that. Yeah, we're going to operate. So this is a function within our system, but we're going to operate upon our system virtual. And if I go back to our detect collision, you'll see that we have these pointers, these 2 pointers for our celestial objects. And what we'll do is we go and we check the corresponding body widget from our system virtual, and then we use this collides with item function from Qt to see if it's colliding with our ptemp inner. And so pretty much this just says if there's an overlay of these 2 graphics items within our scene, then we're gonna, I think, return true for that function. Let me go back to my system. Sorry about this, one sec. And in that event, if we do return true, we see that those objects are colliding. Then next thing we'll do is just compare mass, and if the mass is less than or equal to, we're going to mark our celestial object as destroyed. Likewise, we're going to mark the body widget, which is the buddy that we link to our celestial object. We're going to mark that destroyed as well, so that later our threads can go and process that and destroy our our object. And lastly, we'll just sort of keep track of what we, the amount of objects in our system. So that is the detect collision function. So we haven't removed anything from the system. We've merely ran a detection to mark objects and body widgets that we'll need to destroy later. So that is the first of the threads. The second one is this process here, this process function, and this is where we actually calculate the new acceleration for each celestial object based off its distance from every other object in our environment. So this is a function within our system class. First, we'll go and, so again, we have a double nested loop here. So we have ptemp and ptemp inner. The first thing we do is reset the acceleration to 0. We're going to go and calculate the new acceleration based off all of the other celestial objects within the environment. And then we'll go in. This is just to check that we're not calculating relative to itself. That's why we have this marker. And then if it's not, then we'll run the actual calculation. So we'll go to this here. And so this is one of the many calculations that we have in our nested loop. Pretty much what we do is calculate the distance from that object, again, just using this sort of simple Pythagorean theorem formula, where we're taking sort of the x and y displacement, calculating the angle, because later we'll need to use that angle to reset the x and y acceleration. And then we actually calculate the acceleration magnitude. And again, this is just by using that formula for the force of gravity, where your mass times acceleration is going to be equal to the product of the two masses of interest divided by their distance squared times gravitational constant. So once we have that acceleration calculated, we'll just go and add that to our our x and y acceleration accordingly. So remember, we reset these values to 0, and then since the sum of forces is additive, we'll just go and continuously add these in as we go and process and calculate for every object in relation to every other object. So that is how our second thread works. So now we'll go back to our thread class, and we'll go to our third thread. And this is where we're then going to move, well, based off the acceleration we've calculated, we're then going to update the position and velocity accordingly for our celestial object type. So this won't actually move what we see in the environment. This is going to, again, we're still calculating sort of the raw physics and basic motion mechanics that are going on in the background here. So here we're just simply iterating through our linked list, and each time we're calling this move function, which is a function defined in our celestial class. So first we check, make sure it's not a blue giant, because again, we explicitly don't want to move those objects. And then we're going to go and calculate the, based off the current velocity that we have, we'll end up resetting the velocity based off the current velocity we have and the acceleration we've calculated. We're just going to use this simple displacement formula to check how far our celestial object should be moving within sort of our arbitrary time. So the actual processing is happening every 25 milliseconds. I gave this 5,000 or 50,000, 500,000 number here. It's just sort of an arbitrary number, just so that objects would move, excuse me here, objects would move sort of at a sensible rate within our system. so that it's appealing to the user. So once calculating the displacement from our velocity and acceleration values, we'll then go and accordingly update the current position, or so position plus displacement will be our new position, and then we'll likewise calculate our new velocity, and this is going to be used for subsequent calls of our move function back up in here. And again, velocity is just going to be our acceleration times our time for both our x and y. So that is our third thread. Still some more processing we have to do. We still haven't actually, again, we're just operating on our system. We still need to operate on our system virtual to actually see with our eyes and our environment the movement of these widgets. But before we do that, or before I dive into that, we go into our fourth thread here, which pertains to our orbit type object. So again, these are pretty unique celestial objects compared to every other. You might have noticed that perhaps the orbital path seems a little too perfect. Looks like we maybe fell out of place there. Let me go and reset this. Yeah, the orbital path, perhaps looks a bit too perfect, and there's a reason behind that, which is that we're forcing that planet to stay within its orbital path. Simply put, if I didn't have that force, if I didn't have that forced, then our we simply don't have the processing power to continuously update our velocity and acceleration position quickly enough so it will actually stay in the orbital path. So even though we're providing the correct velocity from the get-go, we simply just can't crunch the numbers quickly enough to maintain orbit. So what we want to do is go and sort of, as it begins to experience that error from lack of process power, we'll want to accordingly adjust the movement of the orbital path so it stays in line and stays at that fixed distance from the nearest star. So let me go into that function here. Now, first, you'll notice we have this, we're using this in orbit true Boolean here, because we don't want to always keep our orbit celestial object in orbit in the event that there's some other disturbance within our environment in which we should break out of orbit. And I demonstrated this before, but for example, I go and introduce another star, then this is going to be a competing mass. We want to acknowledge the force of gravity coming from that mass. And so that's why we have this in orbit variable. So first we're going to check, hey, is our object still orbiting? We're going to, excuse me, and then we're going to go and check, we're going to go and get all these different values here from the star. So we can use this get star again because the orbit class will have a star associated with it, the star that our orbit planet should be orbiting. And then we'll calculate our distance between the star and the orbit celestial object, the theta. And then right here, this displacement is going to calculate the error from our orbital path. Remember, we saved, I mentioned this at the beginning, we saved this radius value, and that radius value is supposed to be the set distance from the star that our orbit object is orbiting. So here we kind of have a measurement of how far off we are, and likewise, we're going to go and calculate the velocity that we should have, and then we're actually going to look at our acceleration magnitude of our orbit object. And this acceleration magnitude is what we use to judge error from our orbital path here. So again, just like with our radius, we have this acceleration value which we've saved from the initialization of adding in our orbit object into our system. And we'll compare the acceleration that we actually have that's currently calculated from all the previous threads to the acceleration we want to have to stay in orbit. And we'll say, hey, if we're within 10% error, then we want to stay in orbit, and we're going to go and fix our path so we stay on that perfect circle. And so that's what's done right here, where, as I mentioned before, this displacement is sort of our error in terms of actual raw position. And then we'll go and sort of subtract that displacement out, and so then our position will get reset, so we're staying on path. Likewise, and then we're just going to go in and reset our velocity based off the velocity magnitude that we should have to maintain that orbital velocity. And again, as always, with respect to our x and y, since we're always processing with respect to both dimensions. Now, say we have error that is greater than 10%, we're going to say, hey, in that case, we likely have another celestial object in our system that we need to pay attention to in order to really follow the laws of gravity here. And so we'll set this in orbit to false. And now we've broken it out of orbit, and now that orbit object will never be really calling this chunk of the code right here again. And then it'll just sort of act just like another planet within the system. So that is the fourth thread. I think the last sort of code I have to dive into with respect to our orbit object. So let me go, I think we have one more thread that I have to cover here. Yeah, and then this relates to our virtual system. And this is where we're going to update the graphical position in our virtual system based off the position saved in our celestial objects within our physical system. So this is updating the position of our body classes, objects. So let me go to transfer here, and you'll see simply we go in for every object, we'll find its buddy, which is again that pointer to its associated linked body type, and then we're just going to set the position. So pretty simple thread there. Now again, we still haven't moved the object in our display. We haven't moved the body object in our display. And so we still have to do that. So let me go back to our GUI.cpp. And that is what occurs right here with this this connect function, where we're just, again, just like our threads, we're linking the output of our timer to this particular function of our system, virtual. It's also called traverse. Oops, let me go, it's pulling the wrong thing here. Go to this, our slot function, so we can receive that signal from our timer. And again, we're going to iterate through our linked list of body objects, and then we're going to move accordingly. That's going to be based off the x position and y position we saved from that fifth thread. And we're pretty much just setting this QRect as a QGraphics type Qt class, and then we're just resetting the position. And then setRect right here will actually move the object, and that's another Qt function. That's what's actually going to move our object in our system, so that's visible to the user. So that is the last part of processing that is done for actually moving all of our objects. So you can see how all those threads and those that one last connect function, all of this here will go in and move everything within our system. Again, a lot of processing, which is why a lot of these we had to use threads. Now, lastly, we have this one last function where we actually need to remove objects from our system if they've been destroyed. So if you recall from the first thread here, we, using that Qt collides with item function, we've marked certain objects and their respective bodies as destroyed. And now we actually need to go in and remove those from the system. So go to remove specific items here. This is within our GUI. And pretty much we end up iterating through our system, and we just check, hey, if it's marked as destroyed, what we're going to go do is first remove from the scene, and then we're going to go into our linked lists and destroy both our body and celestial object accordingly, and preserve links in our system. So let me just go to that function here. So this is we pretty much just recursively call this function until we find the object we wish to destroy and delete. We'll go and set we'll go and preserve our links here, so that when we remove our object, we're still having the previous object point to the next, and then we'll go and we'll go and delete the object from our list, and then still have our linked list preserved. So that is our remove specific items function, and that's where we'll actually remove both our objects and our bodies from our system. These are identical functions right here. And then again, we'll just sort of update the amount of objects that are left that need to be destroyed. So one last thing that I have to cover here is the reset button. And that's fairly straightforward. What we'll do is, again, using this connect, if we ever click our reset button here, we'll call remove items, and we'll use this because remove items is defined within our GUI class. And this is fairly simple, where we just go through, iterate through our entire list, remove it from the scene, and then we'll go and call these two functions and end up sort of nuking the whole system and system virtual. So I'll just go to one of these as an example. Again, they're identical. Again, we're using these Qt classes to avoid interference from other threads. We call this destroy function here, which is defined this one is within our system virtual. And oh, sorry if I back out for a sec. Destroy system. Yeah, we're iterating through our list, and then once we have everything sort of locked, we'll go and we'll actually delete that object type. So that is, I think, the entirety of the code that I want to cover. If you wish to see any more details, please go out and check the GitHub link below associated with this YouTube video, and you can dive through it in more detail and borrow the code yourself and use this application if you have the appropriate Qt functions. So yeah, that's all I have. Thank you for joining, and take care.